So it is my pleasure to introduce you to Carmen Miguel, that I know since many years at this point. And she's a physicist by training, and she was in the area of condensed matter and statistical physics. She got her PhD in '95, and then she's a regular in Boston. She has spent time as a postdoctoral associate on the other sides of the river, so in that little village over there. I don't know. There are a couple of universities on the other side. I don't remember, but you know, so she was at MIT, and working with Maran Cardan, that for physicists you probably know what I'm talking about. And she has been working on many things related to soft and dark condensed matter. Especially dislocation, plasticity, fracture, etc., self-organization and avalanche, and all the how to say, how to connect microscopic properties to mesoscopic properties of materials. And although she was collaborating with many of us that were transitioning into complex network and complex systems, she kept her loyalty to physics until some time ago. And so now she's switching too. And today, Carmen will present some work about flocking dynamics, I believe networks, and how social influence can affect flocking behavior. Just one thing, Carmen will be here for the next 3 weeks until the end of July. So if you have any question, if you want to interact with her, if you want to show your work, please don't hesitate, and she's on the 10th floor. Carmen, thank you very much.
Thank you. Let me start by thanking Alex for his invitation, his kind invitation for us to be here during this month, and for his hospitality. Actually, as he said, we collaborated almost, I don't know.
No, don't say the number. Just a few months ago.
Yeah. I was his postdoc at Trieste, Italy, and I think that it was about time to start doing something again together. And I hope that during this month, with all of you guys, we have the opportunity to maybe start new research directions. And it is a pleasure actually to be here, because I'm going to tell you a little bit about what I've been doing lately. I mean, I was really, very thrilled by the idea that I could maybe move a little bit from the standard physics, condensed matter, as he was saying, research field in which I was working, to this field that is, again, something that it is not very spectacular, but yeah, introduces a little bit more of the complex network knowledge that you all guys have. And I didn't do it because it's not because I didn't like it. I like it a lot, but yeah, because sometimes cannot really afford to do everything. And this time I got maybe more interested in the subject, and that allows me to make the jump into the field. And what I'm going to tell you a little bit is about what we have been exploring. I mean, it's an exploration more than deep knowledge. Probably there will be more questions than really answers to what I'm going to tell you about, which is this flocking dynamics, and how to explore and how to start exploring effects of social influence on the behavior of flocks. I don't know if it's starting here. Well, I'm sure, but still is in the middle. Okay, so this work that I'm going to present to you is part published and part is unpublished, and it has been done in collaboration with a couple of master students, Parley and Javier Cristín, in Barcelona, both at the University of Barcelona and the Universitat Politécnica de Catalunya, and also in collaboration with Romualdo Pastor-Satorras, who is sitting here in the room, and probably will give another talk in a week or so, so you will have some information that is complementary to what I'm going to tell you about today, and different information as well. Okay, so let me start by first, in case, maybe some of you don't know really very well what a flock is, to illustrate that with this beautiful movie that you can find in YouTube. A flock is just a collection of these entities that are able to self-propel, no matter, whether the scale is really micro, or meso, or even macro. These are sheep in the field. And they use very limited environmental information, and actually they interact between themselves using very simple rules to produce what we call a flow, which is a coherent, let's say, state of motion, which is dynamic on the other hand, but it is ordered. And this ordering actually can occur in whatever dimension, in 3D. I mean, there are in nature several examples in 3D and in 2D and actually maybe even 1D. Something that actually is not so common in statistical physics, as I will explain a little bit later. So this spatial ordering that you can see in some of these animals is very amazing, of course, it's very beautiful, but on top of that, I mean, there are many questions that you can ask. And it's how do they manage to really transfer the information and to keep this cohesion in the group so fast, when we know that, I mean, they are not super smart, they don't really have, super brain. And what we also want to characterize is how resilient is this ordered state of motion that they exhibit. These are a few questions, I mean, a couple of questions, but of course you can ask yourselves many more. So let me try to tell you what I'm going to tell you about today, and it's a little bit about what you can find different examples in nature of this flocking. Then I'm going to tell you about the simple models that we physicists use in order to try to answer some of these questions, and in particular I'm going to talk to you about what we call the Vicsek model. It's the simplest model that you could maybe imagine. And then I am going to explain you the modifications that we have implemented into this very simple model in order to have something new that probably was not studied in the literature before. And it's to take into account what we call social structure, and in order to explore what we call behavioral contagion. So the fact that maybe some collective response is emerging in response, as I was saying, to a perturbation that is maybe more local in origin and that can have actually an enormous effect on the field. And finally, I will just finish my talk with some conclusions. So as I said, there are many examples in nature about these flocks in different length scales, from the mammals, the mammal herds, to bacteria colony, and even cells when they, for instance, are repairing damage that we have produced in our skin. They will also kind of flock. Cells, they migrate together as a flock. And it is true that maybe you will see different names referring to the same phenomena, as individuals moving essentially as if they were one. Since, we are not really certain that, there is something else that, there are simple rules that will govern the behavior of these individuals. We cannot really talk about a mind that is collective. Nobody has ever found any experimental evidence of a collective brain or anything like that. We have to rely on what the biologists call senses, the animal senses, the normal senses and biological senses that they have actually at their disposal in order to produce all these beautiful patterns. But it is amazing that, by how using these biological senses, they can really produce changes of direction that are very well coordinated. Or when they, for instance, try to skip an obstacle, it's amazing the way in which actually they move together with such a beautiful choreography that nobody has ever first thought. The interest in the field is more, it goes far beyond from what, it will be just fundamental science, which is by itself something very nice. But also because applications are probably several and in different fields. And in particular, that there is now an interest in the community of scientists in order to mimic biology in what we call synthetic biology. So we want to understand these basic principles that underlie the behavior of such systems in order to produce synthetic structures that are similar in robotics, in computer graphics. Of course, that's probably the field in which the whole thing started. I have this movie here. I don't know if I will be able to switch it on. It wasn't working very well when I was trying. Yeah. So you've seen, probably some of you have seen this movie. Maybe it comes, maybe it doesn't. So I mean, here it doesn't really reproduces very well for some reason. I don't know. I mean, you want to understand all this crowding of people and making special effects that are realistic, and actually this is another application of studying flocking, because you want to make realistic graphics and games, no? And every company nowadays is putting a lot of effort in order to make more and more realistic games, no? So you want to understand also those rules if you want to really become realistic. Again, different ways to describe this phenomena, more physics-like in the sense that, I mean, you use equations of motion like Newtonian, the physics in the sense that, I mean, the particles, the human beings in the particular case, or the animals, will be like atoms or molecules, in a dense system that interact according to some potentials that you have to more or less invent, and then you try to solve those equations of motion deterministically, including some noise, some effects that maybe are good and appropriate for those systems. On the other side, also another physicist approach is to use what we call continuum fields, such as the velocity, the density, and things like that, and to propose what we call Langevin-like equations that are governing the behavior of those fields. It's kind of difficult in here. You could maybe write the equations. It is more difficult, apart from writing them, to solve them. And there is not much actually activity on that side of the board. There are some attempts in this field, but I mean, not so much. Whereas in the middle, probably thanks to numerical simulations, there has been a lot of activity actually trying to understand the basic flow behavior. It means that, I mean, we are going to use agent-based models in which particles will be our agents, in which we introduce some interactions that can be very simple or more complex, as we want. Repulsion, alignment, cohesion are the words that maybe you have to take into account. Plus some local information in the sense that you have to be aware where you are, who are your neighbors, and with whom are you going to interact if you want to have some interesting physics coming out from here. But it wasn't physics, it wasn't a physicist the one that described or tried to propose a model that was simple to start with. It was actually a computer scientist, this guy Reynolds, the one that first proposed a model in 1987 in order to essentially provide, better resolution and better, more realistic looking games, as I was saying before, computer graphics for flying birds, what he was calling voids, birdoids, virtual. So he was actually proposing these kinds of rules that I was telling you that are so simple, such as try to avoid collisions with your nearby mates, and try to maybe stay together. Don't go very far away from the rest, because otherwise it won't be very nice. So there's an attraction towards the center of mass of the group. Avoidance, as I said, and also what is more important is try to keep your motion aligned to the one of your neighbor. Okay? So try to keep yourselves aligned. These are the three rules that were written before and that are actually enough to provide beautiful moving flocks. But still, those interactions were kind of difficult for a physicist because there are three ingredients in which you have pairwise interactions, and then make that the simulations are much lower. So it was at the time that Vicsek proposed his model that the physics community really got very much interested into this field, because in his model things are simplified to the maximum in the sense that he only cares about orientation. So his paper was actually published in 1995, and the main ingredients, you have them on the left of the board, is that you have particles positions that are updated according to this simple rule, just the Euler's dynamics. In discrete times, make the particles advance. Particles live in continuous space, by the way, in 2D in this particular paper, although you could maybe generalize it to higher dimensions. Velocity actually is not even you know, really a full vector in the sense that, I mean, the modulus is kept constant. Can be 1, can be whatever you want. This V0 is a constant. And the only thing that really matters is its orientation that can be all included into what we call phi theta sub I, this angular variable that is defined at the level of each particle. Once you have that, at each time step, the particle, the blue particle sitting here actually looks around itself and finds that there are 3 green particles that are within a given distance, something that maybe this animal can see, even if it's not very realistic, because usually we have eyes that are directed towards the front and not so much towards the back, although there are some animals that really have eyes that are more on the sides and can get almost like very coarse-grained view. But, I mean, he didn't care about that, and he just proposed this radius. Particles that are within that radius are my neighbors, and I will see them, and I will try to imitate them in their motion. I will consider them. If they are outside, I forget about them, and that's it. And with those particles that I'm able to see, I try to keep myself aligned. So that means that my angular variable at the time t plus delta t will be as the result of averaging the angular variable for all those particles that are within the radius. And then, I mean, that will be very boring. I mean, if you just that and a few time steps, everybody will look the same. And in order to include a bit more of realism, what he did actually was to introduce noise. Noise in physics actually has produced beautiful things at different levels, really, from the level of really technical applications, resonances and things like that, to lots of fundamental and statistical physics, new discoveries. This noise is very simple, though. I mean, noise is characterized by this intensity, eta, which is something that goes in between 0 and 1. And then I just generate random variables that are uniformly distributed within the interval minus pi to pi. Why? I mean, because this is an angular variable, right? So I cannot really go beyond minus pi to pi, or between 0 and 2 pi is the same. But the intensity can be more intense, so it can be higher or can be lower. So less intensity means that particles really will get to order very well. High intensity particles will have trouble in order to themselves polarize in a uniform way. Okay. So that's the model, very basic, but still very interesting, and that's why the physics community has produced a lot of papers in response to this very first paper, because it's very simple for us to put in a computer and to study, and to really make very big simulations, including millions of particles, to try to see whether by the end of the day we get something interesting, as you see what we call here this phase diagram, in which what I'm representing here is this letter I, which is what we call the order parameter in physics. So it's just averaging the velocities of all the particles in the system, all of them, normalized by how many I have, and I don't care about really the value of the velocity modulus. So it's just the orientation. And what I see here as a summary of what I'm telling you is a phase transition, what we call in physics a second order phase transition. So something that goes from an order parameter in value which is close to 1 to something that is 0. So that means order, particles really get to travel together in the same direction. 1 means all of them, something in between, not all of them, of course. 0, everybody is free, like an ideal gas to travel in the direction it wants. And that actually happens as a function, as I was saying, of the noise intensity. So there is what we call a critical value of this intensity, for which I see the separation in between the order and disorder phase. I mean, it is not really 0, because as it happens in physics all the time, when you have a finite system, 0 is very difficult to really get. I mean, you have to see 0 in the thermodynamic limit, which means when the number of particles that you consider in your system tends to infinity. Okay, that's what you will get. And close to what we call the critical point around here, I don't know why this scale, I'm sorry, this is a mistake probably that I made. It should be 0 point, or maybe it's quantified in a different way. Sorry about that. Has to be, according to my notation, something that goes in between 0 and 1. And here you see something different, probably because here refers to the product of this and the angle. And it goes from 0 to 2 pi. Sorry about that, because this is my figure. I got it from the paper, from the original paper. But the idea is that below the NC value, which in these units that I'm using between 0 and 1 should be around 0.3, 0.4, depending on the system size, as you will see. You will see this behavior, so it decays from 1 algebraically with this beta power, which we call the critical exponent for the order parameter, as in a ferromagnetic phase transition, the same still, and 0 beyond that. I mean, this is in my work, as I said, this is something that was already in the paper that I quoted. But actually, what you can also maybe try to expect or intuitively expect is that it is not just a matter of the noise, but it is also a matter of the density. So if I have a fixed density, I will have a given value of the noise that will allow me to separate between these two behaviors, ordered from disordered. But if I change the density, that value will change accordingly. Because you can imagine that, I mean, if the system is very dispersed, only a few of those animals are in the field, there are no neighbors, no interactions, no within that radius, so it means that actually the system is going to be disordered all the time. So density is also another crucial parameter. So you can write the relation in this way, you can write the relation in this other way. It's a function of density and keeping the noise constant. You can do both things simultaneously. And then this scenario will be a little bit more rich because you will have another direction emanating from here that will make your phase diagram. But this is in general something that you can find already in reviews. And if you are interested in the values of the exponents and all the numerics up to, great detail, you can take a look at this physical review. That's something for Argentina. Maybe you know them. In which they really work, big numbers, and they provide some calculations with high precision. Already in 2000. Okay, I think that I will skip this. I mean, what I wanted to say in a few words is that, I mean, the fact that you get an ordered phase in 2D, in particular in the Vicsek model, is something surprising in physics. Because in equilibrium physics, which means systems that are not like these ones, that consume energy in order to produce some work. 2D is what we call the lower critical dimension when we are dealing with variables such as these velocities, which are vectors that have a continuous rotational symmetry. So you can rotate a vector continuously around the position in which you have your particle, and this is what we call a rotational symmetry. So systems such as that in physics cannot really exhibit an order-disorder transition at a finite temperature. Temperature in physics will be similar to the noise that I'm introducing into the Vicsek equation, because temperature, what makes is actually disorder the system, for those of you that are not physicists. So there is a theorem actually that is called the Mermin-Wagner theorem that tells you that you cannot find ordered phases in 2D, because it's the dimension below which actually disorder will predominate due to entropy considerations that I don't have probably all the time to explain in the work. But there is a theorem in physics that says that you can have ordered phases. So it was very curious also to physicists to see that in these non-equilibrium systems, you can have ordered phases even in 2D, which is something that is in contradiction to what we know in conventionality. But let me just pass quickly over it. So the important thing here is that, I mean, these systems are out of equilibrium, right? So forget about what physics knows about equilibrium systems, because since they are out of equilibrium, all those considerations actually don't apply. That's it. And the same happens, at different levels in biology, at the level of molecular motors, at the level of bacteria, as I said. So what you have seen is that in this Vicsek model, the order appears as a simple, result of what we call very simple local interaction rules, as you have seen, the alignment rule, essentially. No other information has been used, there is no memory, nothing that is very sophisticated. the question that we were trying to put ourselves is, can we just modify this model a little bit and introduce it? The animals in the end are not so stupid. They have some memory. You know that ants actually have some pheromones or emit some pheromones, and they are able to really go back to the way in which it started if they found essentially food. So there are some mechanisms in nature that actually make the animals not so stupid, but also we don't want them to be very smart. So can we incorporate some extra interaction rules that will allow us to see maybe the same thing but slightly different, or even new things? That was a little bit our starting point. And I went to this summer school and I saw an experimentalist, a biologist that was really showing beautiful pictures. And I thought that maybe one thing to start considering in this field that not so many people had not considered before is the fact that you may have social interactions in between animals. If you have ever maybe wasted your time watching one of these National Geographic videos, the documentary, I like animals, my daughter even more. So you see that groups of animals sometimes travel together, and it's not that they don't know each other. They have some relationships. They are friends. They are family, and they even if they are not within the circle, the Euclidean space, distance that the model, the Vicsek model was set up. They will follow each other because actually it's a matter of survival. If they don't follow the mother, they will die immediately, because first they cannot feed, if they are little ones, or the predators will focus on them. So it's really a matter of survival, to try to make sure that you follow maybe some of your relatives, your mother or whatever member of your group. This is what actually biologists, I discovered afterwards that there is a full branch of biology, or ecology, if you want to call it, in which people are trying to characterize the social networks in groups of animals that are social, because there are animals again that are not social, so asocial. But most of them are social. And they go and characterize them in field experiments and try to see how many connections, how often, how much time do they spend together, and things like that. So there are experimental results that actually will tell you how is the social network of given groups of animals. So it was good that Romualdo was there in Barcelona. He's an expert, as Alessandro and several others in network science. So let's do something about this, because it's nice to put in the Vicsek model some networks. Let's try to see what happens. And that's what we did. First of all, I must tell you that, of course, these networks are temporal, so there is dynamic evolution. There are friendships that are built and are broken, leaders that maybe change, there are acquaintances that are shifting, and visitors that are also coming by, like us, to this group now. So we didn't want to take first all those details into account in the way in which the social network between the animals was going to be, but we integrated all that dynamics in static heterogeneous network, the more general case possible, which is represented here nicely. Nodes will be the animals, and the links in between the nodes, the frequency of their contacts. So since we had, as I said, some experimental data, and here you can see some real network for kangaroos and bison, what we decided to first try is to consider what we call power law heterogeneous, in which one individual has k number of contacts, and the number of contacts is distributed according to this power law with a degree exponent gamma d. And what we are going to do now is just to explore what happens with the Vicsek model when you encode those interactions instead of the ones that I explained you a little while ago, the spatial ones, and systematically as a function of the degree exponent. Because you know that if this degree exponent is very small, there will be maybe a guy with lots of contacts, whereas maybe there will be another guy in which you have only a few, very few. Whereas this gamma d being really bigger means that more or less like a homogeneous network in which more or less everybody will have the same number of contacts. So that's an important and relevant parameter to take into account, and we are going to explore what happens as a function of this degree exponent. Okay? So now my equation of motion will be similar in spirit, but I will substitute the interactions with local neighbors by interactions on the network social contact. So I will be in contact with J if my matrix, my adjacency matrix has a 1 over there and a 0, means that I don't have contact with that individual that belongs to my group. Okay? A group of n individuals that are connected or disconnected according to a matrix that I call the adjacency matrix that actually tries to represent the properties that I have a scale for here. With a degree exponent values. You are more expert than me in that field. So this is a summary of what I get. The same ordered parameter, averaging over the velocities of everybody, according to the new rule. And here is the ordered parameter in the steady state, because this quantity actually moves in time. But after a while, which can be very long, by the way, you will reach what we call a steady state, in which things are not depending anymore on time. We average over that period of time. And we are representing in here the results as a function again of the intensity of this noise that changes a little bit what the interaction will ask me to do. And what I'm representing in here in different colors are different sizes. Okay? The main picture, you have two different values of the degree exponent. This is the group of values for different system sizes that have the same 3.5 degree exponent, whereas in here the degree exponent is 2.1. So it means small and large to me, okay? And what you maybe can appreciate already is that again we have order disorder transition in this case. Something different from 0, something equal to 0. But in here what I see is that the noise intensity for which I see the change is in between 0.6, 0.7. It's a finite quantity, different from 1. And the size dependence is not so huge. Whereas in here, I mean, there is a tendency for that degree exponent that is smaller to see that the order actually disappears at higher values of eta. And that there is a huge, a much stronger dependence on system size. Okay, so two things that we can maybe notice from this one. Here, on the other hand, I fixed the number of individuals in my group, and what I change is the value of the degree exponent passing from the 2.1 that I have here towards the 3.5 that I have on there. So you see this shift that I'm telling you about, the value of the disorder for which you will have the disorder appearing in the system. Nothing very strange. And then I will try to characterize when that happens by means of a critical exponent with the same spirit as in the magnetic systems or in the original Vicsek. So what we physicists do in order to identify what we call finite size effects, the influence of size on the results, is to look at what we call the dynamic susceptibility, which means fluctuations. Fluctuations, how are those fluctuations? And a good indicator of where the transition is happening is the maximum of these fluctuations. Actually, if it was a second order phase transition, what that maximum has to do is to increase with system size in a non-trivial manner. So that's what we did, again, systematically for different values of the degree exponent. And what you can see is that, first of all, the position, as I was saying, is shifting with the value of the degree exponent. And moreover, we see that when we are for degree exponents that are higher, the dispersion, again, regarding system size is not as big as the one that we will have for the gamma d values that are lower. Okay? So that's what I have said to you here in words. So it tends to a constant value that is smaller than 1, 0.6, 0.7, whenever the degree exponent is greater than 2.5. This is what we were noticing. Whereas in the scatter, and you see the evolution with system size is more dramatic. Whenever we go below 2.5, and the shift is to larger and larger values of the noise. So we again propose something that is very common in physics called phase transitions of this kind. The second order phase transition is the finite size scaling analysis. We did that the best we could, with the biggest systems that we could. And this is, in conclusion, what we obtained. Actually, what we saw is that what we call the critical point in the thermodynamic limit, in the limit in which n goes to infinity, you can get it from this analysis for different system sizes. And, well, all the details actually are in the paper that you saw here very fast. It's appeared this year. And I mean, here are the main evidences, numerical evidences that support our main results, so that I'm going to summarize for you here because it's a little bit more technical. And it's that there is this value 2.5 for the degree exponent, below which, I mean, our finite size scaling analysis tells us that, I mean, there is no transition from order to disorder. There is only order, unless you are at eta c equal 1. So maximum disorder. No? Remember that this intensity was maximum of 1, which means actually that whatever you do because of the interaction rule doesn't really matter, because the disorder is so strong that you are going to do whatever the disorder tells you to do. That's it. Forget about the interactions. So what we see is that below 2.5, disorder wins. I mean, disorder doesn't win, I'm sorry. Order wins. I mean, order is what you are going to see, and only when eta is the maximum value, you will see that the system disorders. Only at that particular value. If you're a physicist, it's like having temperature equal to infinity. Only having the transition when temperature is equal to infinity. Okay? Whereas, I mean, if you are above, you will have a finite transition, a transition at a finite value of eta, which is around this value, 0.7. It actually moves with the degree exponent, changes with the degree exponent, approaches actually the value that you will have in this limit, which is 1. So this is the main observation that we saw, not only for the position of the critical point, but also for the exponent. The exponent, you see that evolves, on the other hand, actually with the degree exponent, because it's a finite size effect thing, up to the value 2.5, and beyond that particular value, the critical exponent that we are able to calculate easily from the finite size scale analysis stabilizes around 0.75. Maybe it's not important for many of you because it's very detailed, but I mean, you have to take into account that that helps physicists in order to classify the problems in what we say universality classes. So maybe it is good to explore other systems and experiments and see whether they fall within the same category or different. So it's good to give some information about these numbers, despite they look a little bit detailed. So that's it. And I mean, in words, I mean, what is the conclusion of this piece of work? And is that when the degree of the number of contacts is higher than 2.5, then the critical point actually is there and is finite, even if it doesn't correspond to eta going to 1, which is an enormous amount of noise. This actually represents what we call a mild heterogeneous network. So contacts actually are distributed according to the power law, but I mean the variations are not that high. And then we will end up having this two-order disorder transition in that particular case. Whereas, I mean, if we go to really strongly heterogeneous networks, then what we will see is that the order is the prevalent and the only possible solution. So the ordered phase of the system will be really very resilient, no matter what is the amount of noise that you put in there. Unless you put the maximum amount, the system will stay ordered. And actually, whatever perturbation you make it, actually will rapidly converge towards, again, the ordered state. So you perturb the system, and if you are working under those conditions, the system immediately will go back again to the ordered phase. So the ordered phase is very resilient. And in between, we have this particular value, which is 5/2. No good explanation so far for why that, I mean, but I will tell you in a moment several ideas. And this is what sets up the difference in between the two categories, the two groups. On the other hand, I mean, you may ask, and what animals like to do? Well, it depends very much probably on the measure that you do in order to characterize the social network of the group of animals. So it's not very, you have to take it with some caution. But I mean, what it is true is that we have found some papers in the literature in which they provide degree exponents that change for the group of animals within that particular range, between 1 and 3.5. more experiments will be really needed in order to make this, something more robust. But I mean, this is what there is, and never you are going to reach in an animal group the thermodynamic limit, so you have to live with the idea that the group of animals will be always finite amount of animals. That's not infinite, but it can be really. Okay, so that's the part of the more quantitative work that we did. Let's skip this. Unfortunately, there is no way in which you can really solve that model analytically, but you can solve some limits. You can consider a fully connected network, everybody connected to everybody else, and in that particular case, you can find an analytical solution for the Vicsek model there. What happens is that, again, as in the case of strongly heterogeneous networks, the critical point shifts towards the maximum. It's 1, so the system remains ordered if everybody is connected to everybody else. Not very surprising. Critical exponents are different in that particular case. And I don't know whether you want to know all of that, but for those of you that are physicists, there is this famous XY model, in which actually you have vectors living on the nodes of this lattice. Usually it's squared in 2 dimensions, but it can be in 3 dimensions, it can be whatever. It is interesting in 2 dimensions, and many people claim that the behavior of the Vicsek model in networks should be similar to this model in networks. Okay? And some people already had studied the XY model on networks. It's just an extension of the Ising model that probably all of you know. Ising model, just vector variables that go up and down, that's it. Whereas the XY actually implies vectors that can rotate, as I said to you in the beginning, continuously in the plane, for instance. Okay? That's the definition of it. So it is true that, it's a static network. I have always the same number of neighbors. Why not, finding exactly the same behavior for the Vicsek and his model when living on networks? And what we actually can say is that at least at the level of the critical point, it is not the same. That's the result that you will find in the literature, both for the Ising and for the XY model regarding the critical point. So it is a dependence on this relation between the second and the first moment, which implies that you will have a transition whenever you go beyond gamma d equal to 3 and not 2.4, 2.5. And you won't have a transition because this moment actually is exploding and make the temperature infinite whenever you go below a gamma d equal to 3. Okay? So this is different in our model. We are pretty sure about that. And these results, of course, have been confirmed not only theoretically but also in simulations. But we can also confirm that our results are not the same both at the level of the critical point behavior and at the level of critical exponents. On the other hand, we find that it is more similar, this Vicsek model, to what we call the majority vote model. So this is a model that probably is more familiar to all of you. You have variables that are spin-like in the nodes of a complex network, and they decide to vote against or in favor, up or down, so the 2 states, according to the majority of your contacts. Okay? And you flip that result with a noise, which is what we call here F, which is in the model of the variable that controls the disorder in the system. So in that particular model, actually, there are some calculations done by these people in physical WE, in which they really demonstrate in there 1.2 is the maximum amount of disorder that you can have, because it's the probability of switching, right? So 1.5 will be like our eta equal to 1. Okay? And in there, they have calculated the critical point with some in-field approximation, and they find actually this relation between the moments of the degree distribution, which are different from the ones that you saw before for the Ising of the XY. Okay? So in here, the things will happen as in the Vicsek model that we saw in the simulations. So whenever it's higher than 5 halves, you will have a transition. Whenever it's below that, you won't have transition. And this is the moment that is responsible for that. This will diverge and will make the noise equal to 1/2 when the fluctuations are important, which is in this particular case. Okay? I don't know if it's very technical, but in case, because this field is largely open So I really encourage you to see maybe not animals, but I mean people in the end are kind of animals. So there are many problems that are related to human behavior that can be also maybe coded, with the same idea and the same spirit of the Vicsek model. So you have to look at these things with an open mind, not just in particular for sheep or for fish or whatever. I mean, it's something that we can really use for something more general, which is very nice. And this project is still open, wide. I mean, because we believe that this model a priori is different from ours, but they end up having more or less the same characteristics. Why? Romualdo probably is going to tell you a little bit more about it in his seminar, but still it's open, it's an open issue. In networks, the fact that you have another parameter, a variable that is a vector or a scalar, actually doesn't seem to be so crucial. So here, you have again a reduction in the sense that I'm not having vectors anymore in the majority model. I only have opinions that are can be of two colors, let's say, plus or minus. And despite this fact, the behavior seems to be at the level of the critical point and exponents, not only the critical point, very similar to the Vicsek model. I don't know how much time do I have, Alex, because I have a second part that I wanted also to maybe briefly comment. 5 minutes. 5 minutes. Another thing that we have studied, which is different from what I have explained to you before, is the possibility of having behavioral cascades in these flux. So the fact that maybe an individual or several individuals, get scared, are crazy, become crazy, are more excitated, scared, stressed, whatever, and maybe produce a rearrangement in the system that is not just local, but something really big. In social sciences, those are called behavioral cascades. In physics, we call them avalanches. There are several avalanche systems. Earthquakes, the way materials break sometimes are also represented by those avalanches. Magnetic systems, when you put a magnetic field outside a magnetic system, a magnetic material, and see how the magnetization is increasing as a function of the increasing field, you will see again these avalanches that there are called crackling noise, Barkhausen noise in particular at the level of the magnetism. Very popular phenomenon in physics. So I don't know whether you saw a little bit the movies published as a supplementary material to this paper. It's very nice. But in here, what happens, I can summarize it to you, is that these sheep, as I told you, are very social, very gregarious. They don't really like to be alone. They know that. That's why are so good for domestication, because you can handle them very easily, because you just have to have 5 or 3 of them in front of a big amount, and they will just follow stupidly, actually, even to produce accidents. I read yesterday something funny, because they are so stupid, they are trained to follow, and no matter whether the leader puts them on the cliff, and actually they will follow, and all of them actually will follow and die. It has happened several times, and there are some records of that in the literature. Anyway, so they, in this case, they don't like to be alone, and maybe one of them notices that doesn't have any neighbor around because it was grazing, having some fresh air, and then runs. Immediately, the mechanism that they have for self-defense is to run. And this running actually induces triggers, the movie is now stopped, but you can go and check it, induces a collective motion of all the herd going towards the same direction. Towards the same point, in the space. This is what you saw in the movie. So these are what we call avalanches, and we would like to see whether, our model, the simple Vicsek thing, with some extra, of course, considerations, can produce such avalanches also without the need of, proposing models that are very sophisticated and very animal dependent. Okay, so the normal standard Vicsek model. So what we did is actually to implement this Vicsek model with some extra information, which is the fact that animals may have some long-range sensorial capabilities. They can maybe hear, see, or whatever, depending on the group of animals, and a general concept of leadership. This is something an element, an ingredient that sometimes is brought about in the literature in order to rationalize the cooperative movements of animal groups. The fact that there are leaders that are maybe because of age or because of strength or because they have useful information. The leadership concept that I'm introducing is very general. Don't think about permanent people which are directing the group. No, it can be a switching leader. It can be whatever. It can be very temporal because they have, as I said, very useful information at a given time. And that's what we have introduced in the model. So what we have proposed is to include a leader that has this long-range contagion effect on the individuals, and that he is doing, because maybe he's searching for food, this run and tumble type of dynamics. So I have a leader that has an influence on all the rest of the people. Of course, not only him, everybody else as well. But it's performing such a random path because he's looking for food, goes straight, doesn't find anything, makes a random tumble, and this is something that is again observed in many groups of animals. And you can imagine that if you have such a long-range leader, what you will expect is that since everybody is going to see him, the dynamics is going to be boring. Everybody's going to order and move according to the way the leader is moving. So that is not what we see. What we see is a response in the system that is what will happen with the order parameter in the presence of a leader. Everybody will order, yes. If we don't do anything with the leader, everybody will eventually order with the leader, and this is something that we expect. This is nothing surprising. You break the transition again, as happened before with the very heterogeneous networks. You only disorder when the noise signal is very, very strong. But now we implement this leader that makes this run and tumble. And then what we see is that, depending on the amount of noise that you have in the system, the response is not so trivial. What we see is scale-free avalanches. So sometimes the leader is actually turning, and the number of individuals that are following its turn is just a few. And some others, with exactly the same conditions, but with some noise in there, what we will see is that a huge amount of the group members will follow. And this happens intermittently in time, and with magnitude that it is not trivial. It's not always the same. It's not peak around a given particular value, an average value. This is the sequence of time, and what we have done actually is to first of all, define what an avalanche is. I was saying it with words, counting how many individuals in the group are turning more than a given threshold. And this threshold actually has to do with the noise. So if I have a noise that is bigger, of course, everybody, even if the leader wasn't there, will turn with some value which is proportional to the intensity of the noise. We remove that. And we look at turns that are higher than that threshold that is obviously there because we have some noise. Okay, so look at all the terms that are bigger than this term that is a threshold value. Depends on the noise. Actually, this is a histogram of terms that you will have in a system when the leader is not doing anything and when the leader is making this turn and run and tumble dynamics, open circles. And we only get what we call the tails, when the two distributions actually look very different in response to this leader that is running and tumbling. And we look at the sizes, counting how many individuals are within those tails for different repetitions of the experiment. And the duration actually will be when the signal goes below this threshold, when the number of individuals that are turning is less than this threshold. So this is also something that we do all the time in statistical physics, look at the distribution of these avalanches. There are different ways to do that, the cumulative, the non-cumulative, blah, blah, blah. But the message to take home is that what you see is, again, a broad distribution of avalanche size, a long tail distribution for these avalanche sizes, not only sizes but also duration, something that you wouldn't at least I wouldn't expect a priori, which is nice. In a simple model with only one ingredient, which is that everybody will be able to see a leader that is doing this run and tumble dynamics, I get to see these behavioral cascades that are actually interesting. And this is a characterization, since Ali told me that I only had 5 minutes, probably I have passed over the time. you can do again, the techniques, use the techniques that we use in statistical physics in order to characterize the finite size scaling of these avalanches, both in size and determine exponents that will help other people maybe to compare with those results. And this is what we get. I mean, similar to what happens in other avalanching systems, by the way. And with that, I come to my conclusion. So we have proposed essentially a few modifications we are exploring. There are many more things that one can try, and actually we are trying. You can actually do all these avalanches also in complex networks, something that we are starting now to do. You can put leaders in competition. You can do many things actually to play around games with this. The nice thing about all that in the end is to have experiments. So that's why probably we are also here, because I mean we need to have experiments, and you have data, you have experiments, and it will be nice to make a collaboration in which we explore models, but at the same time compare with experiments. At least to me, it's essential. I mean, I don't really like the idea of making models just for the fun of it. I like to be able to address some experiments. So we have done modifications in the Vicsek model in order to incorporate social structure, the network of heterogeneous social contacts in the group. Actually, we have seen that it's crucial in order to see more or less resilient ordered phases. And we have also incorporated a leader, which is really general in a sense, in order to see the possibility of having behavioral cascades that are scale-free, so of different scales and magnitudes. Oops, I don't know what happened. There is here a missing sentence. Maybe I deleted it without here. Anyway, the conclusion was, as I said, that I mean, if the network of social contacts is not so heterogeneous, is more homogeneous-like, then what you see is that the ordered phase is more fragile. So whatever amount of disorder will be able to destroy. Whereas, I mean, if your social network is heterogeneous, strongly heterogeneous, so you have maybe hub that has lots of contacts and maybe others that are really have very few, it's heterogeneous in that sense, your ordered state is going to be very resilient. So maybe nature works a little bit with that in order to get systems that can get ordered, and no matter what happens, actually recuperate that order easily. It's a little bit our conjecture. On the other hand, the interplay between these long-range sensorial capabilities that some animals may have, together with the presence of these leaders that can influence, for us humans, is obvious, right? I mean, there are such leaders because they dominate the mass media, and they are able to really reach all of us. No? When there's such things are present there, or maybe there are important people in the research community to whom we pay more attention, then what we will see is that maybe the response of a system in which we try to imitate for several reasons can be avalanche-like. And then you will have sometimes changes or opinions that actually will be really distributed among the whole group. And other times those opinions or changes that are happening in society only influence a few of us. With the same conditions, I mean, with the same preparation of the system. If we understand that, I mean, it's interesting to continue investigating along that. But in all of that, I mean, it's really interesting that, I mean, if you have the possibility to maybe make some experiment, just do it, because there is a lack of empirical data that is of quality in order to compare with all these conclusions. So thank you very much for your attention, and I hope that I can
So we have a few minutes for questions, and I have one just to break the ice. It's with respect to the thing of the Melvin-Wagner theorem, etc. Actually, one of the things that we always say is that in a network you are since there is not an actual dimension, but you are in a topological space, you are in the infinite dimension limit. And so all those things shouldn't hold anymore.
It's
if
main
I'm
field,
not-
then,
it's
yes.
main
And then you
field.
don't distinguish.
And then you don't distinguish anymore. So that could be,
A reason
in
why,
a sense, the gamma things that you get is something that is completely different from the classic
Icing
assessment.
or it's Y on networks. We believe it is different. It passed from 3 to 2.5. It is true that maybe it's not so surprising, the fact that you get exponents that are mean field like if you want, or the fact that you don't get like you don't see differences when you implement the Vicsek model or you implement the majority. Because as you said, the fact that you have a two-component vector or maybe just a scalar in this space that is so weird actually doesn't allow you to provoke Goldstone modes, and this Mermin-Wagner theorem actually is not holding here anymore. I don't know if there are Goldstone modes in networks. And how do you excite them? If you could do that, I really don't know.
If you find you have a Nobel Award. So
Nobel Award probably not. No, in normal space, in 2D, what he was commenting, this Mermin-Wagner theorem, it's very easy to understand why you cannot have an ordered phase there. In difference to what I have seen in this model, right? If you have spins that are there sitting on sides, doesn't really matter if it's very ordered or a little bit disordered. It's very easy for a vector that is able to rotate continuously to generate, for this system to excite, to generate what we call waves, magnetic waves, magnons, maybe for physicists. So slight variations from point to point of this vector that is determining my state. And that costs very little energy, as little as you want when you produce these variations in very long length scales. But in networks there is no space. So what is a Goldstone mode in there? That is what entropy will tend to proliferate in order to reduce the free energy cost of different states of magnetism in this case. I don't know in networks how this operates. Maybe there is something similar, excitations that are very close to the fundamental state. If you have a Hamiltonian, maybe you have a Hamiltonian, you can define it. And then you have the ground state, which is what you have at t equals 0, but then you put a little bit of temperature. What is the system doing at this little amount of temperature? How is it exciting itself? And whether those excitations are separated from the ground state by a gap or no. If there is a gap, there is one story. If there is no gap, if it's continuously moving from 0 towards different values of the energy without a gap, will change completely in physics the story. I don't know what about network.
This is the free energy that you should be able to write a free energy.
Well, if you have a Hamiltonian, imagine that you define a model, but in the network, like the ice and all that, and you can
should
do
go to the free energy and then see if the spectrum
what happens
of the free energy.
how do you describe those excitations?
Okay. Yeah.
I don't know if anybody has ever done that. Maybe yes, because nothing is new in this.
He's working on
in
free
Earth.
energy networks, but
Nothing is new. Probably somebody will have ever thought about the problem and is trying to do something. I don't know it. I don't know.
Actually, a question. So I like this topic. Thank you very much.
You're welcome.
The question I have is sort of about targeted noise. So if you wanted to just inject noise into some part of the network, whether it has different effects.
So locally instead of
Yeah.
affecting globally to the
In
system.
a sense, it seems kind of like the role of a leader.
Yeah, the leader actually was not affected by noise.
Oh.
The leader was very, determined.
But the leader
Focused.
itself is kind of causing
But
noise
everybody else,
around it too.
everybody else is subject to this noise. So either because they don't make good decisions, because they have free will, and will tend to do similar but not exactly the same. But it is true. We haven't. No, in physics is what you will call maybe more anneal noise that affects everybody, or quench, in which you may have patches of noise that are affecting differently to different groups or subgroups of the general group. We haven't explored that. Glassiness, let's say, in this context.
That's interesting.
I'm sure the most important application of this in your mind is how in 4 years Spain can win the World Cup. And what I mean is,
Who cares so much about
right. But like certain, I looked at the flocks and I thought of fish and sheep and some of the 2D, 3D. There are many animals that are counter flocks, the killer whales, wolves, and the way that they hunt. And sometimes it's with communication, and other times it's with innate. They look for patterns, just like in soccer. I'm always looking for the triangle. Go to the open space to pass the ball. The same thing with wolves and killer whales. I'm interested in the two flocks, how the smaller flock of predators and large flock of prey, how they encircle, and they see an opportunity to encircle. That's really good.
I haven't done that. I can maybe elucidate about it, but I haven't tried. I don't know anything about it, so it's good that we need to try.
And then is the eta is, I guess, the intensity of the noise, and then there was some angular direction. Is that introduced to does the individual agent perceive that it's just that noise as one of its neighbors?
No. It's a general effect that you have at the level of each individual, and it's not related to its neighbors. And he was asking me about maybe what about introducing some individuals that are more noisy than others?
Right.
Something very reasonable. No, what we have done is to consider the same amount of noise for everybody. And then local interactions with your neighbors. So you are susceptible to the noise in general, but also you are very much conditioned by what your neighbors are doing. Neighbors in a very general sense, either spatial neighbor
I looked at the equation. I was trying to figure out how that noise factor is introduced in the equation. I'll look at it later.
Sorry, maybe I didn't understand.
No, it's okay.
But it's a very plain noise, uniformly distributed, that takes into account the fact that maybe you don't copy perfectly,
Sure.
right? Because in the end we see and we try to imitate, but we don't do it perfectly. So it can be less intense or more intense. More intense will be actually when you are drunk, let's say, you don't focus very well. And less intense maybe in between is something normal, no? Because actually we also have free will, right? And we don't really want to do what our neighbors are. So we want to believe that, at least.
I think it is also just, this is just as a comment, these kind of things have a relevance now in all application related to swarms, and there is the issue that also when you create artificial swarms of robots or micro devices, etc., there is always a noise, and the noise is the fact that you might have transmission that is interrupted for a second with some of the other elements, or you're malfunctioning, whatever. So this is noise might might characterize different things in different contexts.
I have some kilowatts actually sitting on my table on my office in Barcelona, and I can assure you that they're really noisy. It's very bad. The copying system they have.
Okay, so thank you very much
Thank you.
again, Carmen. To get more details on that, just don't hesitate. She's on the 10th floor, and she
You
will
have
stay for several
ideas,
weeks.
data that maybe you want to look at with this perspective. I'm here. We're here for the rest of the month.
Okay,
Thank
and
you.
now I think it's Brazil versus Sweden.
Oh,
So, let's